All right, so we're going to continue our conversation of collisions in one dimension, perfectly elastic collisions. So here we go. Let me go to share my screen and go back to our little view there. Okay, cool. So we were looking at this, and we recognize that in a perfectly elastic collision, there was a couple of things, there's a couple of things that we were noting here, that if we had that this was in one dimension only, that if the work non-conservative was equal to 0 and the net external average force on the system was equal to 0, that we are able to say that it was a perfectly elastic collision and certain equations would be true that we could stipulate and then do some problem solving with, which we'll look at in a couple of minutes. But I wanted to go through a couple of things there. During the derivation of when we use this to derive a conservation of energy statement and this to do a conservation of momentum statement, we got to one point in the problem where we had the following expression, right? This is when we took the two equations and divided them. We were left with this. Now, right now, this is organized by object, by object 1 on one side, object 2 on the other side. I want to reorganize this expression to look at if we look at it with respect to time again. So I have VI1, if I subtract over the VI2, and then I come over here and I have VF2 minus VF1. And we look at that expression, and that should start to, once again, tickle some things in our brains. It's a little weird right now because I've got I1 minus I2 and F2 minus F1. So what I'm going to do there is I'm just going to reorganize one side of this equation to put everything in the same order. Okay. Now, if I look at that, stop the video for a second and see if you remember us talking about a structure that looked like this. All right, so hopefully you figured it out, you restarted it, and you recognized that anytime we subtract velocities like this, this is about relative velocities. This literally says the relative velocity of 1 with respect to 2 before the collision is equal and opposite, because this is vector, so direction, to the relative velocity of 1 with respect to 2 after the collision. But I'm going to reframe that in terms of different language. Okay. So that also could be said in the following way, looking at our picture. So as 1 is approaching 2, the distance between them is getting smaller. The speed at which the two objects approach each other is equal to the speed that they recede from each other after the collision. That's what that says, right? Which is a really powerful notion for a one-dimensional perfectly elastic collision, because there's a certain context that makes sense, right? For example, we'll look at an example where what happens if these two masses are of equal mass, and we'll see what happens there. And I think that will really bring to life this idea of the speed of approach is equal to the speed of recession for any perfectly elastic collision. And that's the sentence that I'm going to write here, which is the expression of what this result means, right? That the speed of approach is equal to the speed of recession for any one-dimensional perfectly elastic collision. So there's that first thing. Okay, so the next thing I want to do is I want to look at a couple of examples and see how we could use our equations in order to do these problems pretty simply. So here we go. M1, M2, VI1. Oh, I don't know what that is. And VI2. So we're going to look at a couple of different samples there just so that we can see what's going on. Let's say that the masses are equal, 10 kilograms, just to make it easy. Let's say initially object 2 is at rest and object 1 is going 5 meters per second positive towards it, because vectors are going to matter here. What happens if they're equal mass? But let's say they're going towards each other. So this is going positive 2 meters per second, so to the right, and this is going negative 3 meters per second to the left, and they collide. We'll see what happens. Maybe we'll look at, a smaller one hitting into a bigger one, 5 meters per second, 0, the bigger one hitting into the smaller one, plus 5 meters per second, 0. And we could do almost an infinite number of permutations of this. But just to see how easy these equations are to use and to manipulate, let's just do these 4 examples. Okay. And then, in the textbook, we'll look at some problems where you'll be doing this problem embedded in other problems. So what I'm going to recognize here is if it's a perfectly elastic collision in one dimension, I'm going to start off with my premise statements. And that is by stipulating it's 1D, the sum of the forces, external average system are equal to 0, and the work non-conserved is equal to 0. If I do that, I don't need to set up the energy equations or the momentum equations. I can just go right to VF1 is equal to M1 minus M2 over M1 plus M2, VI1 plus 2M2 over M1 plus M2, VI2. So I can stipulate that in once I do this. It's like the shortcuts we use for projectile motion when we said, the total y displacement is equal to 0, time up is equal to time down, right? So we have shortcuts that we can assert if we assert certain conditions were met. So those conditions are met, I can put that down. Let's find all the VF1s here, right? So if I look at, let's call them A, B, C, and D. Here we go. For A, this plugin would look like where I'm going to have M1 minus M2. So this whole term is going to go to 0 for this one, right? Because the M1, the two masses are the same. And then for this one, plus 2M2, so that's 2 times 10 kilograms over 10 times 10, or 10 plus 10 kilograms. And then what the initial velocity of 2 is, which was also 0. Oh, so apparently object 1 comes to rest after this collision. Well, that's interesting. Well, let's just go down through the line and do them. Actually, why don't you stop your video for a second, and you can work out what all the VF1s are, and then we'll start and we'll check our answers with each other as I sit here and do this as well. So for B, I've got, once again, this whole term goes to 0. The masses are equal, plus 2 times 10. Well, that's not going to change, over 10 plus 10. That times negative 3 meters per second. Okay. For C, now they don't zero out. So I've got 5 kilograms minus 10 kilograms over 5 kilograms plus 10 kilograms. Times VF1. The second term will zero out because that is going to go to 0. So I've got negative 5 over 15, or negative 1/3. So negative 5/3 meters per second. Okay. And then for D, I've got 10 kilograms minus 5 kilograms over 5 kilograms plus 10 kilograms. Same thing, 5 meters per second, but now it is a positive 1/3. So that is a positive 5/3 meters per second. Okay. The second term will zero out because of VI2 is equal to 0. Okay, so hopefully you got those same results. Then if we're looking at the VF2, once again, I can just assert my equation there. VF2 is 2M1 over M1 plus M2, VI1 plus M2 minus M1 over M1 plus M2, VI2. And if I do the same problem for A, once again here, the second term will zero out because the masses are equal. So this just ends up being 2 times 10 kilograms over 10 kilograms plus 10 kilograms times 5 meters per second, which is just, of course, 5 meters per second. So I can come over here and go plus 5 meters per second. For the second one, the B, it's still going to zero out on this side. That's going to be identical, and that is 1. So this just is 2 meters per second positive. So there we go, plus 2 meters per second. And then for the C, I know VI 1, so 2 times M1, 2 times 5 kilograms over 5 kilograms plus 10 kilograms times VI1, which is 5 meters per second. And I know this term is going to zero out, not because M1 minus M2 is 0, but because VI2 was equal to 0 in this case. And so here I have 10 over, so it's 2/5 or 2/3 times 5, or 10/3, so positive 10/3 meters per second. And then for the D on that, it's going to be identical there because M1 is the same, M1 plus M2 is the same, VI1 is the same, right? So I'm going to get positive 10/3 meters per second, whoops, as our answer there. Okay, something screwy with that. Let's check. Okay. Oh, hold on, that's not right, because 2 times 10, right? So over 5 kilograms plus times 5, so it is 4/3 5 meters per second. Aha, good. 20/3 meters per second. That is going to make a lot more sense. Okay, cool. So we've got this. So let's just look at a couple of things that happen, some interesting things. Notice when the masses are equal, what happens in the interaction? The objects just flip-flop velocities. That's kind of crazy. Notice here when the small thing hits into the big thing, the small thing bounces back, the big thing moves forward, the big thing hits into the small thing, the big thing continues forward, and the small thing goes forward but quicker, right? So some things that happen, those should like physically make sense. But what I want to talk about is that speed of approach is equal to the speed of recession. Well, if we look here, what's the speed of approach? That's 0. So they're approaching each other 5 meters per second. And finally, 2 is receding from 1 5 meters per second. Interesting. So here they're coming together. This is going 2 meters per second this way, 3 meters per second that way. The speed of approach is, once again, 5 meters per second. And what's happening as they recede, this is going way 3, and this 2, that's 5 meters per second, the relative velocity there. Once again, approach at 5 meters per second. What's happening here? Well, if we go, what is the difference between these? It is 15/3, right? Because we would always subtract the velocities in order to see what the speed of the relative velocity is. So negative 15/3 would be the relative velocity, which is, of course, -5, which is the opposite of this. So that worked again. And here, once again, negative 15/3 would be the, oh, so it worked. This idea of speed of approach and speed of recession works there. So that is another powerful way of doing it. So if you have a one-dimensional perfectly elastic collision, we can assert our equations and do them. And you really only need to find one then, and then you can use this logic of the speed of approach equals the speed of recession in order to find the other. And that makes for a nice, simple, easy argument with respect to that. So that's one thing about perfectly elastic collisions. Now, let's talk about what's happening during the perfectly elastic collision. As we said, and we'll use our example here of where VI1 was greater than VI2, and there was a spring in between, object 2, boom, VI2. So what's going to happen here? Well, before the collision, momentum. After the collision, momentum conserved. Energy is conserved. But during the collision, so if I go energy initial is equal to energy during, what we have to understand here is before the collision, I have the kinetic energy, 1/2 K, 1/2 KE, or sorry, KEI1 plus KEI2 is going to equal KEF1, not F, but during 1 plus KE during 2 plus spring potential energy, okay? But let's think about what's happening here. We know that When one hits two, and let's say once again that one is faster than two, one moving faster than two means that that spring will compress. At some point during the collision, though, something very important is going to happen. And that is that that spring is going to achieve a maximum compression. And when does that happen? Well, if you think about it, as long as one is moving faster than two, when it hits the spring, one is going to start to slow down, but two is going to start to speed up. There's going to be one exact moment when, if I'm plotting their speeds with respect to each other through time, let's say here's object one's speed, here's object two's speed, we know that object one is going to slow down, but object two is going to speed up. I don't know if this ends up higher or lower, that would kind of depend on the ratio of the masses, but there's going to be some moment where their velocities are instantaneously equal to each other. And that's the moment at which their relative velocity is equal to zero. And that's the moment that that spring is at maximum compression, because that's the moment that one is slowed down enough and two is sped up enough that afterwards two is going to be going faster, so it's going to start moving away from one. So the point of maximum compression occurs when instantaneously, oh, I can't see that because that's there, instantaneously the relative velocity between the two objects is equal to zero. Therefore, instantaneously, the moment when V1 is equal to V2. Whoops, not V final, right? So if you think about that, what that looks like instantaneously is as if these two masses underwent a perfectly inelastic collision, like they stuck together, because when things stick together, they have the same velocity. So we can find the moment when this is true by doing a momentum problem, assuming instantaneously a perfectly inelastic collision, find the velocity at which that happens. Once you know the velocity at which that happens, can plug that there, and then find out how much spring potential energy exists at that moment. And that's true for all perfectly elastic collisions. There's this one instance where that happens, and that maximum amount of conservative force happens, whether that's a maximum magnetic force that's pushing them apart, but generally it's going to be some nature of elastic force. So there you go. So that's what's happening during the collision. One last thing I want to talk about for nomenclature is perfectly elastic collision is this idea that we have. We also have something that's called a perfectly inelastic collision. So perfectly inelastic, perfectly elastic. I kind of want to talk about the fact that in physics last year, we only dealt with these two things. And we used the words inelastic and elastic, and we didn't put the word perfectly in front of them, but we really ought to put the word perfectly there, because this exists on a continuum. Because we're going to have perfectly inelastic, inelastic, elastic, and perfectly elastic. So what is the distinction? Well, with this, perfectly inelastic is when the objects stick together, okay? And for them to stick together, what means that happened is that there was permanent shape change, as well as their final velocities are equal to one another. But you can imagine a world in which two cars collide and they dent, right? There's permanent shape change. But they don't stick together. That's actually the majority of inelastic collision, right? But I can also have elastic collisions where energy is not conserved. But what do we mean when we say elastic collisions? Well, that's when objects return to their original shape. But energy is not conserved. What on earth is that? Well, I want you to think about a bouncing ball, right? So if I have a super bounce ball, I think, oh, I have one right here. Awesome, right? Super bounce ball. And if I bounce that on my desk here, you can notice that energy is clearly not conserved in the collision with the desk because that ball is not bouncing back up to its original height. But the shape of the ball is not changing as a result of that. So where does the energy going? Well, listen, it's going to sound. If you ever stretch something a lot, you know, it heats up, right? There are certain interactions which are elastic, meaning that the shape of the objects are not changing through that collision, but the total energy of the system is changing because of things going to heat and to sound. And then you have perfectly elastic collisions where the work done by all non-conservative forces is equal to zero. There is no permanent shape change, right? And there you go. And in all of these, as long as there's only two forces or two objects interact, two free objects interacting, I could have momentum conserved during all of them and very different outcomes based on the nature of those interaction forces. Now, I will say in problem solving, if they say the word elastic, they mean perfectly inelastic. If they say the word inelastic, they mean perfectly inelastic, unless the problem is going out of its way in order to do that. Because a lot of people don't use the terminology really effectively. When you get into higher order physics, especially when you get into engineering, material science, you will find out that there is actually a metric that talks about this. And it's something that's called the coefficient of restitution. Okay. Not that you have to know about that, but the coefficient of restitution for a perfectly elastic collision is a 1. The coefficient of perfectly inelastic collision is a 0. And then there are sort of like gradients in between. Like I said, it exists on a continuum. We're not going to live in that space. I'm just saying this for purposes of completion so that when you go hopefully into higher order physics, you don't think I've lied to you. So there's what the book is going to say. We're going to make the assumption perfectly inelastic when they say inelastic, perfectly elastic when they say elastic, and I'm going to try and be more precise on my assessment items. So that's the long and the short of one-dimensional perfectly elastic collisions. So let me stop the share and stop the video.